It's a great pleasure to me to introduce our next speaker. He's James Stanfield from the University of Queensland. And today he'll speak about Hermitian manifolds with Gauduchon connection. Thank you very much, James, for
Thank
accepting
you.
this talk.
Thank you. And thank you for the invitation. Thank you, everyone, for meeting so late. It's nice to see some familiar faces. So yeah, I hope you enjoy. I'll try not to be too technical because it is late in the day, and I know after 4:30 my mind turns off. So yeah, so let's get into it. So the setting is Hermitian geometry. Okay, so we'll start with the setup. And please interrupt me if you have questions or you can't read my handwriting or something like that. That's understandable. So the setup is a Hermitian manifold. So this is an even dimensional smooth manifold with a complex structure and a Hermitian metric. Okay, so if people don't know what that is, let me just very briefly clarify the structure here. So the pair MJ is a complex manifold. Okay, and so that means that M is a smooth, even dimensional manifold. J is a complex structure, so it's an endomorphism of the tangent bundle. It squares to minus the identity, and it's integrable. So this integrability condition can be viewed as this 1-0 bundle being an involutive distribution, where this is I guess the plus I eigenspace of J. For J, when we consider the complexified tangent bundle. Okay. And so all of this is equivalent to M having a holomorphic atlas of charts into Cn. Okay, so you've got all these maps into open subsets of Cn, and their transition charts are holomorphic. So that's what it means to be a complex manifold. And it's just nicer to think of it like a smooth manifold with a complex structure. And G is a Hermitian metric. Okay, so it's a Riemannian metric. And it's such that the J is a linear isometry on the tangent spaces. Okay, so we just have some compatibility with the complex structure there. Okay, and that's what defines a Hermitian manifold. I'm sure most people already knew that. So the most studied complex manifolds are the most studied Hermitian manifolds are the Kähler ones. So we say G is Kähler if the Levi-Civita connection respects the complex structure. Okay. And this is, you might have seen this in other forms, this is equivalent to the fundamental form being closed, where the fundamental form is just G, but we twist by J. Okay, and this is a 2 form on our manifold. So yeah, these are the most well-studied, they're the kind of richest Hermitian manifolds in the sense that what you have is not only do you have a complex structure and a Riemannian structure, but now you have a symplectic structure, right? Because you have this non-degenerate closed 2 form. So it really is the intersection of these 3 kinds of geometries, and you get this very beautiful theory. So, I mean, definitely everyone probably knows this, but the Levi-Civita connection is the one that respects the metric structure and is torsion free. So it's symmetric. Okay, so it's the unique such connection to do that. And so the nice way to visualize Kähler geometry, okay, is if I have two vectors in my tangent space, and I multiply by I or by j. Maybe I'll just write j. And then I parallel transport, and then I do the same thing up here. Then this commutes. Okay, so this is how you would describe Kähler geometry. It's also an isometry at each point, but it also commutes. Okay, so Kähler geometry is quite beautiful, but it's topologically obstructed. So where every complex manifold will emit a Hermitian metric, and it's not too hard to see that, right? To get a Hermitian metric from a complex manifold, take some Riemannian metric G tilde and just take its Hermitian part. Okay. So every complex manifold admits an abundance of Hermitian metrics. Whereas Kähler metrics are topologically obstructed. So, for example, the odd Betti numbers have to be even. Okay, and this comes from Hodge theory. All right, so a nice example is the Hopf surface. Okay, so let's just take the integers acting on C2 minus the origin, and we just we act in the following way. We take n with some complex vector v, and we do one half to the n times v. Okay. And then if we define m to be C2 as the quotient of this, then this is actually diffeomorphic to S1 cross S3. And so what this means is that the first Betti number you can compute from this product is just 1. And that implies that there's no Kähler metrics, right? So very simple construction actually admits no Kähler metrics. And we find this is the case for many, many complex manifolds. Yeah. Is there any questions so far? I'm just kind of running over, just.
Oh, it's okay. It's okay.
Yep. Okay. Okay. So the setting then for us is non-Kähler Hermitian geometry. Okay. So if G is non-Kähler, then that means we need to consider different connections, right? So maybe I'll add an extra implication here. J is not parallel with respect to our Levi-Civita connection, right? So this is not 0. And so what this means is we need to consider more natural connections, right? So Hermitian connections. Okay. So I'll just define this as like a script H. So these are connections. Well, we have a Riemannian structure that we want to preserve. That's fairly natural, but we also have this complex structure. So we want to preserve J. Okay, and in general, this is an infinite dimensional affine space. Okay, so there's no sort of there's no canonical connection that will do this for us. Unlike the Riemannian case, where we have this fundamental theorem of Riemannian geometry, it's very beautiful. Turns out it's not so nice when we restrict to the Hermitian case. And I'll just remark that any connection in here, unless the manifold is scalar, has torsion. Okay, so the torsion tensor I'll define as follows. You take in two vectors and you just kind of commute them like this. And you take the Lie bracket and subtract that off. So that gives you a nice tensor. So you can see if this vanishes for any, so this is usually non-zero, right? If this vanishes for any connection in here, then our manifold's scalar, because then we just have the Levi-Civita connection being parallel with respect to J. Okay. So we could consider this whole space, but it is infinite dimensional, and it doesn't really generalize Kähler geometry in the sense that it doesn't all collapse to the Levi-Civita connection when the manifold's Kähler. Okay. What we want to do is find some distinguished subspace of H that will agree with the Levi-Civita connection when the metric's Kähler, but also remain Hermitian when the metric's non-Kähler. Okay. So this was done by Gauduchon in the 90s, 97. Okay, so what do we have? So what the way you kind of distinguish a subspace of this is you have a natural action, and this is all kind of vague, but you have a UN action essentially, right, on the space of torsion tensors. Okay, so what's this space? Well, it's the torsion eats two vectors and it spits out another vector, right? And it's skew symmetric in X and Y. So this would be the space TM tensor wedge 2 TM. Okay, so that's what I mean by that. And then plus some magic, and by magic I mean representation theory. And this leads to a canonical line of Hermitian connections. Okay, so by a line, I mean a one-dimensional subspace. I guess it could be zero-dimensional in the Kähler case, right, which we'll see. So I'll call this H sub G for Gauduchon. So we have some affine parameter defining it, and we take combinations of the following two connections, which I'll define in a moment. Okay, so this is a one-dimensional space, or at most one-dimensional space of Hermitian connections. They're natural in the sense that they come from this decomposition of torsion tensors by this UN action. The other argument is that G is Kähler if and only if this whole line collapses to a point, and that point is the Levi-Civita connection. Okay, so that's important, because this means that these geometries are generalizing Kähler geometry. Okay. So what are my arguments for this, right? Well, it's kind of natural in the sense it's coming from this representation theoretic decomposition. It's truly generalizing Kähler geometry, right? And the third argument is, I guess, quite an aesthetic one. This line contains all previously distinguished Hermitian connections. So what do I mean by that? So let me point out first the ones that define this line. So for S equals 0, we just get nabla C. This is the Chern connection. Okay, and so this is the unique connection such that the torsion satisfies this. So you can pull J outside of the torsion. And all of these are going to have torsion a priori, so you have to deal with it. And you define these distinguished connections based on torsion. If you want to work in complex coordinates, what this is just telling you is that the mixed components of the torsion vanish, right? So I've nearly given you a proper definition. Now we define this second connection. So this is nabla B, which corresponds to S equals 2. And this is the bismuth connection, sometimes called the Strominger connection. And this is the unique Hermitian connection for which the torsion is a 3-form. This has applications in physics, and it's become quite useful in the pluriclose flow, for instance. So it's nice that it lies on this line. I guess it's not so surprising because it defines the line. So two things being collinear, I guess, is not so surprising. But what's very surprising is that there are many other distinguished connections on this line that all happen to be collinear with these two. So if I look at S equals 1/2, I'll call this the Lieberman connection. And this is the unique connection such that the torsion satisfies the Bianchi identity. Okay, so you take a cyclic sum and it vanishes. So interesting that lies on the line. Yes.
Is there any Hermitian metric important for that connection, for the Lieberman connection?
Yeah, that's a good question. I'm not sure. I know it's important for conformal geometry. When you look at I'm pretty sure if you look at the Dirac operator associated with connection, it's like invariant on a conformal transformation or something. But I'd say this is not so well studied. That's the impression I get anyway from the literature. That's a good question though. I don't know about any special Hermitian metrics.
Thank you.
That's all right. So for S equals 2/3, this is the minimal connection. Okay, and this has minimal torsion amongst all Hermitian connections. So this norm is less than or equal to the norm of T nabla for all nabla in this space. Okay, so that's very interesting. And then we've got one more, S equals 1. I'll call this the Lichner-Rovitz connection. And this is one that maybe might seem quite natural to study in Hermitian geometry as well. It's the projection onto H of the Levi-Civita connection. Okay. So you've got these 5 distinguished connections that a priori didn't have anything to do with each other, all being collinear. Okay, so you got this nice picture here. So this is HG. this is the non-Kähler picture, I suppose. This is S equals 1, 2, 0, 1/2, 2/3. Okay, and then you have the Levi-Civita connection sitting up here. And that projects orthogonally down to nabla 1. Okay, so remember this is bismuth, this is Chern, this is Lieberman, this is the minimal one, and this is the lignorovitz. Okay, so 3 justifications for this line. 1, it comes from this natural representation theoretic decomposition. 2, it truly generalizes Kähler geometry in that it all agrees with the Levi-Civita connection when the metric is Kähler. And 3, it seems to contain already all the Hermitian connections that were previously studied. Okay, so that's very interesting. Let me make a maybe slightly trivial remark. The holonomy of these connections is always in UN. Okay, and this is this just comes from the fact that J is parallel, right? Okay, so you have, if you take the covariant derivative of Jx, it's going to commute with the J, and so you can see that there's a UN inside of your so there's the holonomy is inside UN. Okay, so this leads to first, are there any questions?
No.
Okay, cool. So this leads to a question by Yao in 93. I guess the question is, which compact Hermitian manifolds admit some Hermitian connection with holonomy strictly inside UN? Okay, so with special holonomy. Okay, should use some colors. And then I guess you can go a bit further, right? So in particular, which connections admit holonomy that are discrete? Well, sorry, which Hermitian manifolds admit Hermitian metrics which are with whose holonomy is discrete, right? So flat Hermitian metrics. Okay. So what I mean like flat, remember, so we have the curvature of the metrics being 0, right? So this is defined in the usual way. Okay. So this is already known for a few of the connections. So let me go over that. So here I'm going to always assume MJ is compact for simplicity. But I'll point out when you can drop that. So Boothby in the 50s already studied this question for the Chern connection. So if nabla C, remember is nabla 0, is flat, well, this implies that the universal cover is a Lie group, and the lift of the complex structure is bi-invariant on this Lie group, and the lift of the metric, so maybe I should say this is a Hermitian manifold. We've got 3 pieces of data. The lift of the metric is left invariant. Okay, so what that means, right? This means that it's a complex Lie group. So the group operations are holomorphic with respect to this with this complex structure. Okay, so that's quite nice. So all Chern flat manifolds are covered by complex Lie groups. Okay, and then the question for the
James?
yes, yes.
So G tilde is any left invariant here?
Any left invariant metric, yes.
Any, okay.
Yeah. So maybe I should put an if and only if. Yeah. Right. So,
Thanks.
yeah, any left invariant metric produces it gives you a flat Hermitian connection. So many years later, the same question was studied for the bismuth connection. So this was some work by Yang, Wang, and Zheng in 2016. So the same question, but we replaced the Chern connection with the bismuth connection. So if nabla B is flat, then again we get the cover as a Lie group. The lift of the complex structure is left invariant. Okay, and G tilde is bi-invariant. Okay, so you see that the roles of the left invariants and bi-invariants switch between G and J when we swap to the bismuth connection. Okay, so I think that's quite beautiful that we get this duality here. Remember, if you're a Lie group with a bi-invariant metric, that puts strong restrictions on what you can be, right? You're a compact Lie group cross some Euclidean factor. And moreover, the compact part is going to be compact semi-simple, right? So these are very restrictive, much more restrictive than, say, complex Lie groups. You know, you could, for example, have these nilpotent solvable examples with left invariant metrics. Okay, so it seems that the bismuth connection is much more restrictive, and that just comes from switching the roles of the left invariants and bi-invariants. And so I guess you think about when we look at the Gauduchon line, right, which is the affine combination of the Chern and the bismuth, we're kind of combining these two things. Maybe it's too strong. Maybe we're just going to get the trivial thing. So maybe the cover will just be a torus, i.e. the metric will be Kähler, is what I mean by when I say that. But first, before I state the conjecture, a more general conjecture was stated a few years ago, which requires one small definition. Okay, we call a Hermitian connection Kähler-like okay, if its curvature satisfies the same symmetries as a Kähler metric, right? So first, if we take the cyclic sum of three vectors like that, so this is the Bianchi identity. And second, it satisfies this type condition, meaning it's kind of this Hermitian operator, right? So, which I'll call a type condition. Okay, and this is for three vectors x, y, and z. Okay, so this is clearly more general than flat, right? A flat metric will obviously satisfy this because the curvature vanishes identically. But somehow there's been a lot of interest in studying these Kähler-like conditions, so we studied that as well, and there's a conjecture that was already stated. So let me state the conjecture, which is the main problem. So it was made by Bo Yang and Fengyang Zhang in 2018. So this was for the flat case. Okay, and then Angela, Orta, Ugata, and Villacampa, which I can't fit in. Also in 2018, this was for the Kayla-like case. The conjecture states that compact Hermitian manifolds with Kayla-like nabla S. Okay, so this is the Gauduchon connections. Kayla as long as we're not in one of these two cases already studied. So remember, S equals 0 and S equals 2 is already covered by these theorems. And so as long as you're not 0 or 2, the claim is that this is Kayla. Okay. So yeah, the claim is that this condition is just too strong. It just forces your metric to be Kayla. Okay. So let me just quickly mention some previous results. Okay, if you're on a complex three-dimensional solved manifold with this canonical bundle being trivial, then the conjecture holds. Okay, so then this was by the authors of the conjecture, Angela, Ortel, Ugata, and Villacampa in 2018. If nabla S is flat and n equals 2, okay, this was also covered by Yang and Zheng in 2018 as well. If nabla S is Kayla-like and we have this very strange interval, S is not in this very weird interval. I mean, this just comes from solving a certain quadratic equation. So it was solved for most of the real line except for S between these two. So I'll just give the approximate form of these numbers. Okay, so this was by Yang and Zheng in 2018, but also Zhao and Zheng in last year. Okay, so this was for the flat case, and this was for the Kayla-like case. Okay, so it was known for most of the line, but not this interval, which also contains all the distinguished connections, right? Or almost all the distinguished connections. So all the interesting cases are in there as well. What else has been done? If nabla S is flat and M is a Lie group, so this is not necessarily compact. And n equals 2, or the torsions parallel. Then this was solved by Vezzoni, Yang, and Zheng in 2019. And then, so what else is known? So I've mentioned the flat case for the Chern and Bismuth connections, but I haven't mentioned the Kayla-like case, right? So it's kind of understood for the Bismuth connection. So if the Bismuth connection is Kayla-like, then this is equivalent to the metric being pluriclosed and the torsion being parallel. Okay, this is by, again, Zhao and Zheng in 2019. And then I should mention that the churn case is still open. So so far we don't have any non-trivial examples. So no non-trivial. And by non-trivial, I mean ones that aren't already churn flat. We have an abundance of them, and ones that aren't Kähler, right? Obviously, a Kähler metric is going to be Kähler-like. So there's no non-trivial examples here. I'm not going to make a conjecture either way, but I suspect maybe there will be. But that's, I don't know, that's just a conjecture on feeling, so not too much evidence. Anyway, so let me state the main theorem. I don't want to run out of time before I can actually state my result. I should ask if there's any questions on this. I know I went kind of quickly through the previous result. Okay. So this was a theorem by myself and Ramiro Lafuente. This year. So let's I'll try and state it in a fairly general form. Let's let this be a Hermitian manifold. Okay. If we have a Kähler-like Gauduchon connection, for S not equal to 0 or 2, and either two things hold. One, well, if M is compact, or S is not equal to these two values, well then the manifold is Kähler. Okay, so in particular we solve the conjecture, right? So the compact case is what was conjectured. So for compact Hermitian manifolds with Kähler-like nabla S, the claim was that it was Kähler, so this covers that. And we almost get the non-compact case, right? So as long as S is not either of these two values, then it's Kähler. So let me just let's recall what these two mean, right? Recall that for S equals 2/3, this is just the minimal connection. Okay, but there's no known interpretation for nabla 4-on-5. So it's a little bit mysterious why this 4-on-5 is there. I would maybe expect 2-on-3 to show up because it's this nice distinguished connection. We haven't so far observed any nice geometric properties of nabla 4-on-5. Okay? But yeah, somehow it shows up as an artifact of our proof, and I'm not sure if there would be counterexamples. Are there any questions on the main theorem? Okay. So let me just mention a corollary. It's not of the theorem, it's of the proof. So essentially what I'm saying is we can say things a little bit more, slightly more generally. If we have some action by holomorphic isometries, okay, such that the quotient space is compact, or the orbit space is compact, then the same conclusion holds. Okay, so what I mean is you can, if you take a Hermitian manifold, nabla S is Kähler-like, S is not equal to 0 or 2, and you have an action with compact orbit space, then the same conclusion holds. Okay, so in particular, if the quotient is a point, okay, so this is a homogeneous space, then the same conclusion holds. So I spent a few weeks this year trying to find counterexamples on Lie groups, and unfortunately, it's not going to work, because if you've got enough symmetries, then the same conclusion will hold. In fact, you can't even look at. I mean, it excludes quite a lot, right? So as soon as you've got a compact orbit space, you can't look for counterexamples. So it's going to make life a little bit difficult going forward. What I would, I guess, as a future direction, right, is if I want to look for examples here, I guess I want to look at things of this form, right? So either the quotient is R, or the lines are in infinity. So I want to look at these cohomogeneity 1 examples to try and find maybe some flat or Kähler-like examples for S equals 2/3 or 4/5. Haven't had so much luck with that so far, but it's fairly.
So James,
yeah.
So in the corollary, you don't need the quotient to be a manifold.
No, you don't.
At all.
Yeah.
Okay.
No. Yeah. The reason is because this proof is just we look at a real valued function, and we say if this function attains a maximum, then everything goes through. Okay. So if your quotient is compact, and this function is geometric, right? So it's going to be invariant under these symmetries. If the quotient's compact, then it's going to attain a maximum, and so that the whole proof goes through. So you don't need to appeal to the fact that it's a manifold or not. Okay, so I've got a few minutes left. So maybe I'll talk a little bit about the proof. But before I do that, are there any questions? Okay. So I'll try not to make this too complicated, because I know it's now past 5. So I know it's a bit of a sin to do mathematics past 5. So let's take TS. We'll just call that our T nabla S, right? So this is the torsion. Remember, this is this. Okay, and we'll just call T the Chern torsion. Okay. And again, we'll take this to be R nabla S. Okay, so we complexify our tangent space, and we write it into the plus or minus I eigenbundles of J. This is fairly standard. So J will be I and minus I on that decomposition. Now, so what do I want to do? Unfortunately, we have to work in a frame. So we take a local unitary frame. So these are, these satisfy this. Okay, and we consider the dual frame as well. This is just notation. So a very important one form we have to consider is the trace of the torsion. Okay, so this is sometimes called the torsion one form. So we take the trace of the torsion. Okay, sometimes called the Gauduchon form as well. The real part of this is the Lie form. So by definition of the nabla S, the idea is we can write the torsion Ts as some linear function in the Chern torsion. So this entire line, right, the torsion is given by some combination of the Chern torsion. You can see that when the Chern torsion vanishes, the line collapses to a point. So this is fairly intuitive, right? This just comes from the definition of nabla S. So for example, if I want to look at this, then this is just 1 minus S times T EI EJ. Okay, and we've got some S factor as well. Okay. And so the idea is we want to write derivatives of the covariant derivatives of the torsion in terms of some function of the torsion. Okay? And the way we do it is with the Bianchi identity. Okay, so what this means is that the cyclic sum of RS X, Y, Z is going to be the cyclic sum. And then what we have is, so for a general Bianchi identity, right, we have the following. This is, so it's a little ugly, but this holds. Okay, so this holds for any connection with torsion. And so the idea is, right, Kähler-like will imply this equals 0. So this is the Kähler-like condition. So we're asking that the Bianchi identity holds. And so what we can do is with some algebraic tricks to get rid of the cyclic sum, right? So Kähler-like, what we want to do is get the covariant derivatives of the Chern torsion. This ends up being some quadratic in the Chern torsion. So remember the S torsion I can write in terms of the Chern torsion, right? So these can all be turned into T's as long as I bring out S factors. If this side is 0, then I can essentially solve for the S covariant derivative of T and get some quadratic in the torsion. So we can turn derivatives using Kähler-likeness into algebraic expressions. Okay, so an example would be 2 times 2s minus 1. So we get kind of this divergence term. Remember, this is a trace of the torsion. This gives s squared norm t squared plus s times 2 minus 3s squared. Okay. So in general, what am I trying to do? So we've used the Kähler-like condition once, and what we want to do is use it a few more times. And the way I'm going to do that is by considering second derivatives now of the torsion. Okay, so if I take one covariant derivative, I get a quadratic. If I take another covariant derivative, I get a cubic. And then I'm going to use the fact that I can write curvature in terms of second derivatives, and then use the Kähler-like condition again to get some more identities and then get the rigidity required. Okay. So in general, remember, I can write the curvature as this commutator of second derivatives. But I need to remember that these connections have torsion, so this comes out, but that's not so bad. And so what that means is that if I act the curvature tensor on the torsion tensor, what do I get? So I get Yeah, so I mean, it's going to be effectively second derivatives acting on t, which means instead of quadratic terms, I get cubic terms. Okay. And so now if I look at the Kähler identities or Kähler-like identities applied to this side, I'm going to get some algebraic identities in T, and then I can get the right rigidity out. So I'll consider contractions of, and we go a little bit higher order, T cubed tensor eta. Okay, so this turns out to be the right thing to do. So these are going to be functions. For example, C, which is the most important one, is the norm of this contraction here, squared. Okay, and these all map from M into C. In general, A and B are complex functions. C is clearly a real function. Okay. Okay, cool. So, yeah, as I said, so contractions of now the curvature RS tensor eta, okay, well, these are going to give a linear system for A, B, and C. Okay, so we take contractions of this tensor, okay, and use the Kähler-like identities, and we're going to have certain things equaling 0, and we'll get a linear system in these functions, and the goal is to show that this system is overdetermined and that at least C vanishes, because once C vanishes, the proof is easy. Okay, so maybe I won't show all of the equations we do, but maybe just some examples. So the first equation, for instance, is this one. This is actually just a first order computation, so we don't have to. I mean, this was essentially already known. So these P1s and P2s are polynomials in S. So we get a linear combination of B and C. The second one, I guess, is more important that I want to highlight. The Bianchi identity implies what? So 0 is the same as, again, CS is just a polynomial. This is RS, EI bar. So we're tracing eta sharp bar. And then the Kähler-like condition means that I can swap, what am I swapping? Let me just make sure. I can swap this and this. So the Bianchi identity plus the type condition is giving me this. No, that should be EI. Okay, and so you can see now, because I essentially have formulas for RS acting on T, right? I can directly compute this, and I can directly compute this using those formulas. And so I get 0 being some polynomial in S times A plus some polynomial in S times B plus some polynomial in S times C. And there's a fourth function that we have to deal with, but that's okay. It's this function, right? So it's the derivative. Okay. Okay, and then the third one is the type condition, right? So this implies that RS of EI, EJ is always going to be 0, right? Because this is Hermitian, so the only way this could be non-zero is if there's a bar there, but we leave no bars. Okay, so again, we get 0 is C of S squared, RS, EI. We get that, and again, we get like another linear combination of A, B, and C, and so on. Okay, there's a fourth condition, right? So using the type condition. Because I'm close to time, I won't write it out. But again, what this leads to is some matrix, depending on S, times the vector A, B, C, and this auxiliary function. This has to be 0. And then it turns out the determinant of this, which took some months to get right, is 64 s to the 8th, s minus 2 cubed, s minus 1 cubed, 2s minus 1 cubed times 3s minus 2 squared times 5s minus 4, which looks horrible, but the fact that it even factors like this is a miracle. Okay, I find this amazing that it comes down like this. Mainly because it took so long to get the computations right to have something that nice. So let me just quickly detail how the rest of the proof goes. So if M is compact, then that means that the maximum of this function, the norm of eta squared, is attained. Okay, say some p, and then this means the derivative equals 0, and so this function is vanishing. Okay, and so now you have a 4x4 matrix times this. You know, the system is overdetermined, right? So this implies that the system overdetermined. Okay, and this implies that C equals 0, and that's enough to get Kayla, right? This implies that T eta of that thing equals 0, and then if you take the trace of that, you get eta is equivalent to 0, and the proof goes through. Okay, it's not so hard to go from there. That's quite easy. The key is showing that eta vanishes everywhere. And then I guess you can see that for M non-compact, and S, S not in the roots of that polynomial, you also get the same thing going through, because now this matrix is invertible, so you get, for instance, that all these 3 are 0. And so I guess it leaves a few cases, right? So S equals a half, 1, 0 and 2 we're leaving out, right? So we don't have to worry about that. 1 and a half are quite simple. This was essentially already done, but we are left with these two mysterious values, which again, I find it quite mysterious, but very interesting nonetheless. And I mean, so I'll probably finish there, but the obvious direction is to look for examples here, right? To look for flat or Kähler-like examples, or possibly fill in that remaining case. Beyond that, it would be maybe interesting to look at like special holonomy of these connections. So so-called Gauduchon Calabi-Yau could be quite interesting. I mean, there's a lot of places you could take this. But because I'm over time, I'll leave it there. And if you have any questions, let me know. Thank you again for letting me speak. Thanks.
Thank you very much, James.
Thank you.
Is there any question? Can you hear me?
Yes.
Mm-hmm.
Is there any question?
So the line, this special line, you don't have a definition by a property of which is satisfied by or exactly by those connections in the line.
So once so kind of defined by the torsion is what you're asking, or something like that. Some property of the torsion that defines the line. There is, but I didn't write it down because it takes a little bit of time. But you can decompose the torsion into like these 2, 0, 1, 1, and 0, 2 parts. it turns out this is always precisely the Nijenhuis tensor, so this vanishes for a complex manifold. And then you can decompose this further into T, B, and TS. So this satisfies the Bianchi identity, I think, and this is the orthogonal component. And then the canonical connections satisfy T1, 1B being 0. And you also prescribe one other part of the torsion. Can't remember what the precise component is, but you prescribe it to be something like 1 minus S on 2 times the derivative of the Kähler form, something like that. The way I prefer to think of it, right, is the torsion of S. We want to prescribe it like, what am I trying to say? Well, yeah, I mean, you're essentially writing, like, I would say any Hermitian connection is determined by the 1-1 part, so it's determined by this part of the torsion. Okay, and it's just a bit of algebra to show that. And what you do is prescribe this Z bar. So you prescribe the torsion to be, well, what data do we have associated to a Hermitian manifold, right? Well, you could take a scalar multiple of the Chern torsion, right? So, and the way you combine it here is with Y and Z. Okay, so this will determine the connection, and it's just, you just take some scalar of the Chern torsion, and hopefully that's a little bit more insightful. Yeah.
Oh, thank you.
That's
And
okay.
is the connections in the line, they have can have different geodesics?
Yeah, I think a priori they do. The Bismuth connection has the same geodesics as the Levi-Civita connection, I think. I think this is a general, yeah, I think this is a general fact about connections with skew symmetric torsion. They have the same, like if you, yeah. But I think a priori for the others, yeah. I've looked into this and it's not very well studied. So I would love to learn more about that.
Thank you.
Okay.
James, for
One
this,
question.
for these two special numbers,
Yes.
is it known that in the flat case they have to be Kähler?
No. Yeah, this is still open.
Oh, even in
Yeah.
the flat?
Even the flat
It's
case,
open.
yeah. Yeah.
Okay. And
Well,
so,
I mean, for non-compact, right? Compact, it's done.
non-compact, yeah. And for all these numbers other than 0 and 2,
Yes.
what about Ricci flat? Has Ricci flat been studied for?
Yes, so I've a new preprint coming out with Kyle Broder looking at this question. The thing with Ricci flat is, I mean, there's a lot of things just looking at the Hermitian part of the Ricci curvature, right? So essentially we have an abundance of examples satisfying this. Okay, so the Hermitian part of the Ricci curvature, say R per S, equals 0. So I showed with Kyle Broder that actually on the Hopf manifolds for S in, I think, minus infinity to 0, not inclusive. Actually, sorry, 0 to infinity. So there exists on the Hopf manifold, so S1 cross S3. Okay, so there are an abundance of examples, at least with the Hermitian part vanishing, right? But the full Ricci tensor, there are also many examples. So if you look at any balanced, say a compact quotient of a complex nil manifold. Okay, these are Chern flat, but these are also balanced, and so all the Ricci curvatures agree, and they all vanish identically.
I mean,
So that's
no
another reason.
Chern and no bismuth. I mean, for these other parameters.
Yeah.
If
No, yeah, but they all vanish identically on
okay.
compact. Yeah, all the Ricci's vanish. Yeah.
And for bismuth, is there any conjecture? Something like Ricci flat plus something implies scalar?
That's a good question. I don't think so. Not that I know of. Perhaps
Okay.
there should be.
Thanks.
It's all right. Thank you.
James, one question. Is there something known about the holonomy of a Keller-like connection? Is it always a proper subgroup? Can it be contained in SUN?
That's a really good question. I don't think so. Not that I know of. I think I would have possibly seen that already if I could. One interesting problem that was solved recently is if I mean, this doesn't really answer your question, right? But on a Weismann manifold, the holonomy of the bismuth connection is in what am I doing? UN-1,
Yes.
which is really interesting. Yeah. Which yeah. I mean, is that your result? Did I? Sorry. I think I got it right.
Weismann is the second scalar-like in dimension 4, I think. Or something like that.
Is it already Kähler-like in dimension 4? Yeah, maybe. I don't know. It's a good question. Yeah, I don't know.
Okay, well, thank you.
That's all right.
Any other question? Thanks. What is love? Thanks again.
Thank you.